Bismillahirrahmanirrahim. Welcome back to my channel. Back for the video. It's been a while. It's been a couple of days. I haven't uploaded any video. This video is going to be all about QPSK, QAM, and we're going to try to generate the signal using GNU Radio. Also, at the same time, we will also try to transmit this using our Osmocom sync, also known as the device that I'm using is actually HackRF. Let me walk you through with the flow graph, how simple this flow graph is. So I'm using 4 random sources. Each source is going to depict a different type of modulation source input. For example, I have QPSK, then I have QAM, then I have 16 and 1064 and 16 and then 1024 QAM. So these are 0. You have a random source that is actually going from 0 to 2, and the number of samples that is generating is going to be 1000. And same thing goes for 4, then 8 and 16. Number of samples which are being generated is about 1K. Now I'm using a selector switch. Now what this switch allows me to do is allows me to actually select the type of modulation that I want. It allows me to actually select, okay, do I want to take this input and then take this input to my de-interleaver block, or do I can select out of these 4 inputs, I can select one of the inputs, so I can use that for different modulation. Once I do that, then it's going into a de-interleave block. What this block actually does, it actually provides sort of multiplexing. You have multiple inputs, you have about 1000 samples coming in, and it's going to split that into a multiple stream, and this is exactly what's going on. Now this is going into a corrector to float block. Why? Because this is sort of providing amplification. So whatever the sample, let's say a sample number 1 comes in to this block, it will multiply this by 1.5. So sort of like providing like an amplitude to whatever your incoming signal is, samples are. Then it's going into a float to complex block. Float to complex is just converting this from real and imaginary. So basically, if you were to think of it, this is I and Q. Basically, that's what it is. That's all there is to it. And then float to complex block. And then I'm using virtual syncs, a lot of virtual sync and sources that I'm using. So I can produce a signal within that flow graph, and then I can call that flow graph by using a source block and just calling it the same name. And then it will act as a source for the next part of the flow graph. Now, if you were to look at this, now you have virtuals, this signal which is being just prepared into complex. This is going to an add constant block, and notice the value that I'm using is -1 - 1. Basically, this is providing me sort of like a BPSK, phase shifting modulation type of a thing, where you have different points at different location on I axis and Q axis. So this is sort of that. This is exactly what it's doing. Then I'm trying to repeat these samples again by providing an interpolation factor of 20. So this is sort of like an amplification. And then it's going into a virtual sync, which I'm calling signal 2. Now this is where everything takes place. Next, the signal 2 is being fed into a root race cosine filter, which is a very essential filter when you are trying to generate a higher order modulation schemes. For example, like QAM in our case. So this is basically the root race cosine filter is an important filter. Why? Because I use this to reduce ISI inter-symbol interference between your signal, because you will see the spectrum and then you will know what I mean to say when I see the what I meant to say with respect to ISI samples symbols interference. Now also this also provides me to actually do the so my signal should limit within that Nyquist criteria or Nyquist limit, band limit. Second, so basically up till here, this is basically your transmitted signal. Now receiving side, you got to have a root race cosine filter. So this is the receive part of your signal, which is using also a root race cosine filter. This is also being injected into a GUI time sync. And after GUI time sync block, this is also going into virtual sync. And then all of these, then after that, this signal is also being sent to a selector block, and then from that selector block it's being transmitted using an Osmocom sync, which I have connected my HackRF to, And then all of these inputs that you're seeing, these can be visualized either using your time sync, frequency sync, or your sync. So this is basically the idea behind this particular flow graph that you're looking at right now. So now it's time for us. So let me run this flow graph. So you would see. So basically what I'm doing, I have Osmocom source, which is going to transmit this signal. And then at the back end, I also have my GQRX, which is also running. So I'm going to transmit this signal at 435 megahertz. So when I play this signal right now, this is what you're seeing right now. This is exactly what you're seeing right now. Okay, this. So this is what you're looking at right now. I have just simply connected my RTL-SDR dongle, and we're visualizing this. This is what's going on right now. I haven't transmitted a signal because I haven't played this flow graph yet. So this is what you're looking at right now at 435 megahertz. Now the next step, just leave this thing running, and then I'm gonna transmit using my Osmocom source. In our case, is going to be HackRF, and I'm gonna play this flow graph. Now, wait for it. Wait for it. Here we go. So right now, which is being transmitted at 435. Let's quickly look at my QPSK signal. We're going to start off from QPSK. This is what a QPSK signals look like. Right now, this is what you're visualizing at QPSK. All right, notice this. These yellow lines are like quietly spread out because you need to look at this, because when you compare this to, let's say, to other higher order modulation schemes, you would see these lines like all shrunk. This will, like, fade out. As you can see, these lines are much darker. But watch this. What happens when I change the modulation? Let me change this, because you see these yellow lines. These are all the way up till here. All the way up till here. Now let me change this modulation scheme to 16 QAM, and notice the difference. You would these lines are going to be faded out as compared to what you were seeing earlier. Why? Because higher modulation schemes, your symbols or your bits are very much packed together as compared to a lower order modulation scheme. So let's look at 1024 so you can see the difference. So this is what you're looking at 1024 QAM. expand this flow graph, and as default 16 QAM. We're also monitoring this on GQRX, and this is what it looks like at 16 QAM, guys. Notice that you see these lines. They're like quite spread out as they are spread out, quite spread out. But when you go to a higher and higher modulation scheme and a lower to lower modulation scheme, this will spread out more. At higher modulation scheme, this will shrink. These yellow lines will shrink. Let's quickly look at 1020. Let's look at QPSK, because these are the two main extremes that we have. Quadrature phase shift keying, where you only have 4 constellation points, 1, 2, 3, 4. And you have 16 QAM, you have 16 points, 16 main points, these blue points, 1, 2, 3, 4, and then 16. Then you have 64 QAM. So you got to count these blue points, 1, 2, 3, 4, 5, and so on. And then you have 1024 QAM. This is what 1024 QAM looks like, because they are very close to each other. So let's quickly look at our GQRX. So 1024, let's look at QPSK first. And let me quickly go in. This is what QPSK looks like. All right, you can clearly see these yellow lines are quite spread out. This is where I have changed the modulation type. So this is right now whatever you're visualizing QPSK, quadrature phase shift keying, and you can see these yellow lines are quite further away. What I mean to say is this, because when you're using lower modulation schemes, it packs less bits, because the number of levels you will have, you'll be taking 2 bits, and the maximum states that you can do is 2 raised to 2, which is going to be 4. And when it comes to 1024 QPSK, let's change this and let's look at our spectrum. Again, this is where I've changed the spectrum. Now these lines here, they are like faded out. As you can see these were like a lot of yellow lines. These are just fading it out. Now, when you look at 1664 QAM, you will see this spread further. So this is where I've changed this modulation schemes. Now you can check and see this. So more and more start concentrating on this main lobe of your spectrum at higher modulation scheme. When it comes to lower modulation, it's spread out much further. And the reason being that when you're close to the base station, adaptive modulation encoding scheme allows you, which is a 5G and 4G, in real 4G and when 5G, it allows you to basically to have higher data rates when you're closer to a base station, and further away, you will use a lower modulation scheme. So you will get like data services, but not as fast as you're supposed to get when you're using 1024 QAM. So that's the basic idea behind these modulation schemes. So if you like my video, thanks for watching, and don't forget to like and subscribe to my channel, and thanks for watching.